So now we will consider an example. So let's say we have a signal. So whatever the following is very important topic. So in structure, this is the core of structural dynamics or any other vibration course. So this concept is very important. So now let's say we have some periodic signal. So periodic signal, so which is f of t, but when limit of time goes to infinity, f of t becomes 0. So that means this signal can be anything. So this signal can be like this or like this or some random. So it will decay when the t is very large. So this could be any signal. So what we are doing, so we take this signal, we take this entire signal, and whenever it signal is starting here and doing its part, so whenever it going to decay end, so we will chop little bit and we are repeating the same signal again. So we are repeating the same signal again, then we are chopping it when it's trying to end, then we are repeating the same thing. So likewise, so with that we take this time period as t. So now we are saying this has this signal is f of t is periodic with the time period of t, f of t. So we convert into in this signal, aperiodic signal, into periodic in this step. So once it becomes periodic, we can represent this f of t in terms of Fourier series. So we can represent this in Fourier series, for example exponential Fourier series. So f of t will be summation n equal to minus infinity to plus infinity. So where the definition of Fourier series complex form, so yeah, this one. So cn will be, so cn is some constant. So exponential of I into 2 pi t will be the time period into n into t. So this is the exponential form. So exponential form of Fourier series. Now I am considering the system. So here this is only a signal. So signal applied to this spring mass damper system, right? So now I am writing equation of motion. It is not 0, it is f of t with the boundary condition x of 0 equal to x naught, x dot of 0, x dot naught. So this one has that definition, x t goes to infinity, f of t goes to 0. So this is called aperiodic, not periodic function, but we converted into periodic. So therefore we can write that function in terms of Fourier transform. So minus infinity to infinity, so 1 divided by 2 pi e power minus I omega t, so d omega. So we converted this, we have represented this f of t in terms of frequency. Similarly we represent x dot and x double dot in Fourier transform. So x of t will be, so instead of, so it's a very simple thing. So then we need to take derivative of this with respect to t, right? So then if we take, it becomes 1 divided by 2 pi minus infinity to infinity minus I omega, then x of omega, then we take double derivative of t, 1 divided by 2 pi minus infinity to infinity. This is I square become omega square, so I plus this will be minus x of omega e power minus I omega t d omega. So now we substitute, so we substitute all these things. So we substitute all these things into the governing equation. So thereby it converts the governing equation of time domain becomes governing equation of frequency domain. So mass of, then if we do it, so how it will become minus m omega square minus m omega square, then it becomes minus I omega c plus k of x of omega, x of omega integral 1 divided by 2 pi minus infinity to infinity d omega equal to 1 divided by 2 pi minus infinity to infinity f of omega e power I omega t d omega. So now we can club the integral. D omega of x of t, this will be x of omega minus f of omega into integral d omega equal to 0. So therefore whatever, so d omega cannot be 0, so this bracket becomes 0. So then it becomes m minus k omega square I c omega of x of omega equal to f of omega. Therefore x of omega equal to f of omega divided by k minus m omega square minus I c omega. So this one, so this equation is very important one. This equation is governing differential equation in frequency domain. So whereas this one is governing differential equation time domain. So this equation is get converted into this form. So therefore we can write, so by rearranging the term, we can write x of omega in terms of h of omega into f of omega, where h of omega is 1 divided by k minus m omega square minus ICW. So this one is more familiar to you, because when we write the time domain result, this is the frequency domain result. So left part is frequency domain result. So whereas in time domain result, time domain for periodic excitation, for periodic or harmonic excitation, so we have solution of this form x of t. I am writing the particular integral term. So when it becomes steady state, it becomes xst, static deflection, divided by, so k minus m omega square, so not in this form, minus IC omega. So into e power I omega t. So this one and this one is exactly similar. So whereas this x of t is written capital X into e power I omega t. So this part and this part is very similar. So what we can conclude from this point, so if we, whatever the experiment you are doing, whatever the analysis you are doing, whether you having a system, for the system you have, you can give harmonic excitation and sweep and get the x, which is 1 divided by k minus m omega square minus ic omega. You can get this one and you can calculate the h of omega. So because it is same, so h of omega is same. And you, second one is you can give impulse function or aperiodic wave, and you can get the, for you find the response x of t, then you take Fourier transform of x of t, so then you get the response in the frequency domain, which will be equivalent to x. So which will be equivalent to x is the amplitude which defines the amplitude in the time period domain. So if you are not clear in this, in next step you will get some little more clarification. And this x and h of omega, this value is called dynamic stiffness. This dynamic stiffness is function of frequency. It is only the function of frequency. So depending upon the frequency, this dynamic stiffness will vary. Because of dynamic stiffness is varying, the system amplitude is increasing and decreasing depending upon where the natural frequency is placed. So from this, what we are concluding is that for time domain, so there we have an equation mx double dot plus cx dot plus kx equal to f of t, which is the differential equation. Whereas in frequency domain, we have x of omega equal to h of omega equal to f of omega, which is algebraic equation. So which is very simple than differential equation. So to get x of t from x of omega, so we just need to take inverse Fourier transform. So to get this, so we have special algorithm that is called FFT, fast Fourier transform, which will calculate this Fourier transform quickly. So it is optimized for fast calculation. So therefore, by using this Fourier transform, we can switch to time domain to the frequency domain and frequency domain to the time domain with simple mathematics.